My sister-in-law sent me a note about the tape. She listened, so she must have listened to the tape episode, and then I got a WhatsApp message about the tape, and it was like just totally random because she doesn't like text me,
Right.
you know.
Right.
She texts my wife every day. They have this little what's that word game, Wordle. So
Wordle. Oh, they're still playing Wordle, huh?
Oh yeah, I told them don't play Wordle. Like the New York Times is mining all your data and stuff.
Yeah,
And
right.
they're like whatever. She texts me, says hostage tape for over the mouth is used for those with sleep apnea. It encourages nasal breathing and limits snoring. So that's the name of it.
She's
Hostage
gonna
tape.
use hostage tape. I told you, it's a thing.
So I'm not sure. So I'm not sure if she listened to the episode and was like, mouth tape. I'm gonna go check that out, or if she already knew about it and then So
that's
anyways,
crazy. Yeah.
So for Kim, thank you for listening to the tape episode, and hostage tape.
Right on.
I think that's a weird name for it.
It's creepy. It's super creepy. I don't think I'm into that at all. Right, but okay.
Okay. I don't know. Maybe I'll try that. I don't know. We'll see. Anyways, all right. So the other night, I'm talking to the youngest about the tape episode because we talked about the tape. I think it was coming back from swim or something, and came up the inspiration for that one was one of the other kids. Right. I was talking about my daughter. She needed tape. We talked about tape. And so the youngest, she says to me, she wants me to do something that she suggested. And she says, you should do one on the light bulb. I'm like, yeah, of course. The light bulb. I sort of laugh at that. I say, yeah, that's a good idea. So she gets excited. She wants to know that, I'm crediting her in the episode as the inspiration.
Well done, youngest child.
There you go. There you go. So she gets excited, and told her we'd do it. Okay. But then I'm thinking, what am I going to say about light bulbs? Because it's sort of this, for kids, it's probably something that they hear a lot about. Thomas Edison and filaments and glass and, it's all like, and people, this is like well-trodden area, right? So people know this stuff. So I started thinking about it, and I realized this past week, I'm actually kind of hugely nostalgic about glowy lights. I love glowy lights.
Yeah.
There's something about it. I don't know how else to say it, really. It's like one of these early memories. And I think about Disneyland. I love Disneyland. It's that like that.
You do.
That glow of Main Street, right? Christmas lights. And I love drone shows. Anything that's got glowy or blinky lights. I've got a little red LED on my microphone here. I'm just like, I love it. And,
the data center blinking red and green lights.
I know, exactly.
Right?
The little lights. Okay, so for me, it's got a lot of like nostalgia here. But the very first glowy lights that I remember came out of this like blue plastic case. All right. It's one of those 150-in-1 electronics kits. And I don't know if you had one of these, when you were a kid, but
I'm a girl. Yeah. I had a Barbie.
I wasn't going to say that, but
yeah, okay, but go ahead.
But we're of the generation that we're like gender stereotype toys.
Yes, we did.
And so it was one of those, but it was like you get it at Radio Shack or something, right? And it was like this little board, and it had a bunch of like electronic components on this board, and there were little springs popping up on the whole board. And basically what you do is you take these little jumper wires and you lift the spring a little bit, with your fingernail, and you jam this like exposed wire in, and you make circuits. You kind of, connect it all in. You don't do any soldering or anything like that, but you have this little book and you build little electronics things, calculator, an alarm, whatever. But the way that you knew that it was working was this little red LED that was up on the top, and it would glow, and if you got it right, that little tiny LED would do it. So, you get it all together. And if you got it wrong, it didn't light up. I didn't really understand what a diode was. I couldn't have told you about current flow or anything. I mean, I remember this, I was a little kid, but I understood if that little light turns on, the circuit was at least sort of correct. So looking back, I don't have like these strong memories of incandescent bulbs from childhood, but these glowy, small, tiny, blinky, lights. I remember LEDs.
Okay, I do too. I had one of those Coleco handheld football games. You know the one where the interface you're looking at looks like a stadium, but the actual piece of it that
Yeah.
glows is only teeny tiny, and then it has the football lines on it,
Yeah.
and then it's two defenders and like someone who obviously has a ball because you can't throw it. You're always running, right? And you'd run back and forth, back and forth, back and forth, and until everybody got all caught up and then you'd run, right? And you're just clicking buttons like, go, 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 go. 9-volt battery.
beep,
It
beep,
lasts
beep.
for beep, 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 beep. It just keeps going, right? Like, yes, no graphics, no screen, really. Just little red dashes going up. And it was a football game. And then, like, the next year you got the good one. It was when somebody else played defense. So there's someone on that side, there's someone on this side, and you're both, like, trying to hold it steady while you're... It was great. You tilt it, get the angle right, because if you hit if the light hit it wrong, you couldn't see anything. But I remember being completely obsessed with that thing. It was just blinking LEDs, and I got to tell you, that was enough.
Something in the cool of it, something I missed, shifted in the quiet. When we were like this, you're like warm light, soft in the night.
Beep, 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 beep. All right, folks. Hello. Welcome to another episode of the Nostalgic Nerds Podcast, where we talk about history of tech and what it teaches us about the present and the future. Tonight, we're talking about LEDs, light-emitting diodes.
Before we get to the nostalgia, we should explain that a light-emitting diode, what it actually is. At its core, it's a semiconductor device. A diode means current flows in one direction. When electrons move across the material and recombine, they release energy in the form of photons. There's no real filament. Nothing's heating up until it glows. The light comes directly from electronic transitions inside the material. The color depends on the energy gap of that material. Different materials emit different wavelengths, and that's the mechanism. That's why my Christmas tree can be 1,000 different colors, all on the same light strand. That's why.
I love the Christmas, the Christmas LEDs, man. I'm trying to switch all of them over to that. Yeah, it's better. So LEDs, that's not some overnight thing then. How did it develop?
No. The phenomenon was observed in 1907 by H.J. Round. I'm going to look him up because I bet he looks like a nerd.
Just like, what was that? Richard Drew or whatever his name was.
Yeah, his name was. He was super nerdy. Loved his glasses, though. He noticed certain materials emitting light under current. It didn't go anywhere at the time. But in 1920s, Oleg Losev, sounds like someone who would stalk me, honestly,
maybe.
Studied it more seriously. He even suggested signaling application, but vacuum tubes dominated that era. The first practical visible LED was demonstrated in 1962 by Nick Holonyak. Oh, that sounds like holodeck. Like, that's pretty good, right? That's good. It was red. It was dim. It was expensive. Red dominated because the semiconductor material engineers could reliably manufacture, like gallium arsenide, naturally emitted in the red and infrared range. The band gap determined the color. Green and yellow took longer, and blue was the real obstacle.
Okay, so we're going to talk about blue, but it just dawned on me for a second here, like those infrared ones, like, remote controls on TVs used to be corded. Well, it was the little, infrared LEDs that switched that away from being corded.
So you could lose it because it was no longer tethered to the thing it worked with.
Well, and then people would put cords on them and like attach them to the couch and stuff. All right. So tell us about why was blue so difficult?
Well, blue light requires a larger band gap. That meant working with materials like gallium nitrate. Gallium nitride was extremely difficult to grow in high-quality crystalline form. High defect densities reduced efficiency, so for years, blue emitters were dim and impractical. Researchers kept working on substrate materials, deposition techniques, and doping methods, but it took decades. And we don't mean doping like they were getting high and trying to figure it out.
No,
I mean, maybe
definitely
they
not.
were, but I don't think
Well,
that's it.
Well, no. All right. So, all right. I love the blue diode stuff. So this is kind of where it'll get a little nerdy. I apologize. So
Oh, it wasn't nerdy up until then, huh?
it was just a little nerdy. It was just a little nerdy. All right. So on paper, gallium nitride should work, right? The band gap is right for blue. In practice, crystal growth was the bottleneck. We'll get talk about this in a second here. So with the crystal growth, you have dislocations, defects, all kinds of structural issues that killed efficiency. Because there's got to be mass scale, right? You can't just you grow a crystal and make it work, but you got to grow thousands and millions of these things. So, all right, here's where it gets technical, but it is important. So, a semiconductor's band gap. So that's what we're talking about, like the difference between one side of the circuit and another. The difference between the energy or the band gap is the energy difference between the valence band, where electrons normally reside, and the conduction band, where they can move freely and carry current. When an electron crosses the gap and then recombines, the energy released can emerge as a photon. And the size of the band gap determines the wavelength, and therefore the color of the emitted light. Red light requires a smaller band gap than blue light, which is why early materials naturally produce red. To make efficient LEDs, the semiconductor crystal, the actual crystal, that's why they have to grow these, it has to be grown with very low defect density, because imperfections in the lattice of the crystal disrupt electron movement and provide non-radiative pathways where energy is lost as heat instead of light. You want more light instead of heat. High-quality crystal growth is therefore not just a manufacturing detail, it directly determines brightness, efficiency, and reliability. And coming back to the practical now, okay, so that was a little like semiconductor, nerdiness. In the late 80s and early 90s, Shuji Nakamura at Nichia, so it's a Japanese company, refined techniques for growing gallium nitride layers with much lower defect densities. Improved deposition for crystals, better doping strategies. So by the early 1990s, high brightness blue LEDs were commercially viable. Once you have blue, producing white light is straightforward. So up until this point, LEDs, like the closest you could get to white would actually be yellow. So to get white, you need a blue emitter combined with a phosphor coating that shifts part of the spectrum into longer wavelengths, and then your eye goes, oh, well, I believe that is white. And that's how most white LEDs work today. So this is a big deal. That's as big a deal because this guy Nakamura, along with Isamu Akasaki and Hiroshi Amano, they received the Nobel Prize in Physics in 2014 for that work. So a large part of foundational LEDs, the IP and the manufacturing, actually remains with that company, Nichia.
Entirely in that company in Japan. Like they own LED.
Yeah.
Wow.
Like blue LEDs, which is super, like you can't have white LEDs without this blue technology.
That's crazy. As white LEDs improved, they started showing up in places where lighting runs constantly. Places like warehouses, hospitals, streetlights. Those are environments where lamps stay on for long periods, and where replacing them is a logistical exercise, not just a trip to a drawer in your house. An LED streetlight can operate for tens of thousands of hours before noticeable degradation. Incandescent bulbs don't operate in that range. High-pressure sodium lamps last longer than incandescent, but they still require periodic replacement. By the late 2000s, cities began retrofit programs. Utilities offered incentives. Commercial buildings upgraded in stages. Congress had so many meetings about What? We have to change our light bulbs? I mean, it was ridiculous.
That is ridiculous.
Of course we have to change them. Quit being dumb. Like, early, early LED installations grew criticism for color, temperature, and glare. Those issues were adjusted over time. Yeah, you know what? You couldn't get a soft white bulb. You got the kind of white bulb where you could see the bones in your hand, right? Like really, really white. Manufacturing scaled. Cost per lumen dropped. Every time Sam looks at something and says, it's 1,500 lumens. And he's like, I have no idea what that means. Every time he says it to me, every time, I have no idea what it means. And I remind him that 1 lumen is 1 candle light. 1,500 represents 1,500 candles. So yes, right? So cost per lumen dropped. Efficiency improved year after year. Now, in most new construction, LED is standard.
All right. So, look, before we go on, we should talk about the headlights. We should talk about the headlight issue. They're too freaking bright.
Honestly, you're right. You're right. I don't understand why I have to be blinded by large SUVs every time I'm going down the road. And you know what, though? I'll have to say this. Cybertruck, not so great. Right? I'm never blinded by a Cybertruck. It has LEDs. I don't quite get it. Are they using Christmas lights in there? I don't know. But a Suburban, and the thing that kills you is the stupid things are only 3 inches long. How did they get so bright? Like, that's crazy. You stare at the headlight while you're driving and you're like, I can't see anything anymore, period. They're awful. They
are awful. Here in the UK, I think regulation in the UK and Europe was a little bit like a few years ahead of the US. So you didn't start seeing like some of the really obnoxious LEDs in the US. We already had them in the UK for the last 10 years or something. But like, I live out in the sticks. There's no streetlights. There's like one lane roads.
I live in the desert. There's none here either.
And they're so bright. They're just, I can't see the potholes in front of me when there's a car coming. They're so darn bright.
I can't see anything. I'm like, and then if you're behind me, I have to like just move the rear view mirror. I'm just because I'm going blind from the back. It's all awful. It's all awful. But at the same time, on the dark desert roads at night,
yes,
I'm glad I have them. Right? I'm kind of glad.
On a dark desert
I don't know
highway.
what to do. With
the cool wind in your hair.
Yes.
LEDs blasting. Yeah. So I think there's a lot of advantages, right? But I got to say, like,
don't you wish they were smarter? Like, but they made them so that you can look around corners. Like, they flip back and forth to look around the corner. Why can't they just tilt down when they realize they're coming up on like, a roadster that is only 3 inches off the ground? Like I don't understand that. I don't understand. Like, we have so many SUVs in the U.S. Like for some reason we default to gigantic car. Well, we're Americans. We like bigger's better. And so like, yes, of course I drive an itty bitty SUV, right? With LED lights.
Of course.
But I'm probably blinding someone in a Miata, but what do I care? Like, at the end of the day, right? Like, I think they should be smart enough to like tilt down, right?
Yeah.
Just tilt down so that you don't blind oncoming traffic, especially. I mean, if we can have sensors that can drive the damn car for you, how come it can't just do that? It can turn my windshield wipers on when the windshield like feels rain, but it can't do that? No. Lexus, no. Like, figure it out.
They're Japanese. They could figure this out.
They got the stuff. Like,
they got
the
stuff. I mean, like, one of the problems with LEDs in housing residential use cases has always been directional versus diffusion, right? So LEDs are super, super directional. And it's because they lay them out on a board, in a circuit board, and they stick the diode on there. And it's just a little tiny little thing. Mm-hmm. Right. But it's super directional. So they've developed strategies to diffuse them. So I'm thinking like with headlights, well, directional should be an advantage, right? Because then you could choose to turn on and turn off which LEDs and the directional array that you create so that you're not blinding the stupid car in front of you, but you're lighting up the path around the car. Like, you got radar in the cars for collision detection and all that. It should, like, LiDAR, right? It should detect the car in front of it and say, I'm not going to shine the lights right there on that car. I know it's a car. I don't need to blast it. Shine the lights
Right?
on the, out, like, in other places where the car is not.
I
I
know
don't know.
U.S. auto manufacturers are under a little bit of stress lately, but I'm just going to put it out there. Maybe you could help us out. Like, eventually, just kind of help us out. Maybe not this year. I get tariffs and all that, but like maybe in a couple years.
Couple of years.
Help us out.
Like,
Yeah, help us out.
I figure software plus hardware, like we've seen this pattern many times, right?
Software
Hardware.
plus hardware equals solution.
Yeah. Yeah.
Right?
Okay. There's got to be a software solution to this problem here. All right. So coming back to this, lighting still represents a meaningful portion of global electricity consumption. As LEDs have replaced incandescents and fluorescent systems, and, what was the big deal? Like, people in Congress, saying, "Oh, we'll bring back incandescents." Like, really? Come on.
Like, what? Well, you know why? Because they all own stock in utility companies.
Yeah.
Like, and the more money you spend on your electricity, the more money they all make. Like, let's not be like that's exactly what it is. And go ahead.
Yeah,
they're
I
ridiculous.
know. It's like,
Well,
it's just
and for like the last, so like not the last administration, but the administration before, it was like low flow toilets. Like, can't flush
yeah.
them, can't flush the toilet, and now we're back to toilets again and
Yeah.
paper straws. So who the hell knows, right? Like, they have
Whatever.
to complain about something, and so they complained. This year it's pennies, wind turbines, and we're back to toilets. So we'll see how it goes.
Okay. Well, we'll see. It's high to the high beam lights now. That's my thing. And I feel like
Fair
I'm Clint Eastwood, telling the kids to get off my lawn. So, yeah. Anyways,
We
all
are.
right. So,
We're that age now.
I know we are. LEDs replaced incandescents and fluorescent systems. Energy demand for lighting has declined in many regions, even as the number of light sources has increased. Incandescent bulbs convert much of their energy into heat. LEDs convert a far higher portion into visible light. Still, they have heat, though, but it's a different problem. Anyways, that difference multiplied across billions of fixtures affects grid demand, hopefully in a positive way. There are environmental effects as well. Reduced electricity use lowers emissions, where grids rely on fossil fuels. Good. LED lifespans reduce replacement frequency and waste. Okay, all right. So I've got LEDs everywhere in the house. They still burn out. Like, it's not like they're, perfect. And it ticks me off because this feels a lot like planned obsolescence. Because I know that a well-engineered light, LED light, could last a very, very long time. And so because it's me, I one of them burns out. I pull it apart, pop it off, and see where the diodes are. And then you could see the circuit board. And then you go like, wait, what happened? And they put crappy heat sinks and crappy resistors and stuff on the board, and they just burn out. It makes me mad. Anyways.
Dude, you only paid like $4 for it. What do you want?
Yeah, but you know what? Like, if I paid $7 for it, then they would last 3 times as long. Yeah,
but then they would be lasting like 15 years. And how do you make money on that? Like, they guarantee them for 5 years, right? And I think 5 years is like enough that I have very high ceilings. Like, for me to change a bulb, it really is rough. But at least I only have to do it once every 5 years, right? Yeah.
True. All right. So, look, the phase out of mercury-containing fluorescent lamps changes disposal dynamics. Like, that's a good thing. So, there's a lot of positive environmental impacts out of LEDs.
There are economic implications. Maintenance cycles are longer. Municipal budgets adjust. Commercial lighting designs shift toward integrated LED fixtures rather than replaceable bulbs. Manufacturing capacity is geographically concentrated. Gallium nitride wafer production, phosphor chemistry, and LED packaging technologies are clustered in specific regions and firms. LEDs are no longer novelty components. They're embedded across infrastructure, residential, commercial, industrial, automotive, aviation, digital displays. The industry continues moving forward, though. Efficiency gains continue, though we're closer to theoretical limits in production.
One thing that's on the horizon is micro LED displays. Instead of backlights or organic emitters, Microscopic inorganic LEDs act as individual pixels. Manufacturing yield, I know, isn't that cool? Like,
That's crazy.
it is crazy. Manufacturing yield and mass transfer remain challenges, though. A gallium nitride is increasingly used in power electronics. High-frequency gallium nitride transistors appear in compact power supplies and chargers.
Lighting systems are becoming networked. LEDs integrate with sensor controls and building management system. Dimming and color tuning are standard capabilities. Yeah, you know what? You can go to Home Depot and get a light bulb, and it's got every color in it. And some kind of crazy Bluetooth crap where you can just change it all the time. I don't know.
Do you have any of those?
I don't, but every Christmas I see them and I think, why not? Like, why not? Like, that'd be fun. Like, put them outside. That'd be fun. There's ongoing research into new semiconductor materials, improved substrates, phosphor stability, and advanced heat management. There's debates about light pollution and blue-rich lighting. There's research into circadian lighting and human biological response. Yeah, my whole life runs by my circadian rhythm. Like, I'm sleepy when the sun goes down, wide awake when the sun comes up. Like, it is very, very well tuned. And I think it would be cool if my bedroom lights could trick me. Like, could I sit in my bedroom with the lights on and my brain could think at 9:00 at night it's still light out, and then I set the lights to change their hue, right, to eventually make me sleepy and put me to bed at 11 instead of 6:30. Because that's where I'm like in the winter, I'm like, oh man, it's 4:30. I'm so tired. Like, I'm not tired. This is stupid. But the sun went down, and so now I need to go to bed. It's just bad.
You should try living a little further north. It's even worse here.
Yeah, see, that's terrible. At any rate, the techniques developed to grow and process gallium nitrate for blue LEDs now underpin a range of other devices, from fast-switching power transistors to RF amplifiers and emerging micro-LED displays. Using LEDs for medical sterilization and water purification are two concrete outcomes of that research. Well, that's good. It's cheap, right? Like that's good.
Yeah, I think that, I mean, who doesn't want pure water, right? Who doesn't want, sterilized, hospitals? Like,
Yeah,
that's
but
pretty cool.
if you used to do it with chemicals or UV, right? Like, now you get to do it. Well, so I have this thing where you can stick stuff in it and then you close the lid and it's UV and it sterilizes stuff. So, any of my, like, toenail clippers or micro needles I use on my face, like, all of that needs cleaned in a very extreme way. What do you got there?
I guess this is my UV LEDs right here. I have that UV curing resin,
I use that to put my nails on.
Yeah, isn't that?
Yeah.
It's so slick. They're like, oh, I'm gonna blast you.
Yeah, no, I have one. It's like a big dome and you stick your whole hand in it. Yeah, it's good. And it gets a little warm because there's so many of the LED UV stuff in it. So I mean, like, I use it. Definitely we use it a lot anyway, right? Like, yeah, that's rad.
I think this is a lot of cool, future developments there. It's particularly in the sort of medical and water stuff. I was doing some stuff with this foundation, and their big thing is water. Water safety and water stability. And, I think that they're considering different, UV and LED solutions to purify water. I think it's cool.
So when I worked at Forrester, I would have clients in pharma, and they would talk about how in third world countries, like they said, like, the meds we have, like would actually work in third world countries, right? Like, they could cure dysentery, they can cure HIV, they can, or at least make it really treatable, right? They could do all that, but some places they don't, because the water's no good. Like, the first thing you have to do is get people clean
Fix the
water, right?
Yeah.
Yeah. And it's like, how do you do that in an economical way where, you don't have to bring to bear water treatment facilities? Well, this is how you do it, right?
Yeah.
It is super important. It is, like, maybe not for me yet, but yeah, you know what I mean? No, it's really, really important. So
I wonder, I mean, I have seen some of those like portable purification kits, and they include, different lights and stuff, and it feels a little bit like, snake oil or something, but
Could you imagine
does,
if it was just a light bulb? It was just a
I know.
light bulb, and now you're drinking contaminated crap because you bought the cheapo one on Temu, right? Yeah, it's exactly what. Like, I should have paid more than 75 cents for it.
Right.
Yeah.
The LEDs kill COVID. No, you can't believe that. Oh, but wait, they do. Oh no. Yeah. Anyways, all right. So look, from a tiny red dot and a plastic kit to streetlights and aircraft cabins, it's been a long arc. I didn't know what the band gap was when I was, lifting those little springs on that kit with my fingernail. I just knew that the light came on when I got the thing right. So now most of the light around us isn't coming from something burning. It's coming from semiconductors doing exactly what they're engineered to do. And that's probably enough LEDs for one night. So if you enjoyed the episode, please take a moment to like, subscribe, share, do all the clickings and all of that. It genuinely helps other people to find us. If you have ideas for future episodes like this one, or just want to say hello, you can reach us at Nostalgic
Nerds Podcast at gmail.com.
There you go.
Thanks, everybody, for listening. I hope this was nerdy enough. I feel nerdy.
It was pretty nerdy.
I feel nerdy.
Gallium nitride, valence bands.
Right? It was super nerdy. Thanks for listening.
Thanks, everybody. Have a good day.
You hold your shape, you don't lean in. There's a distance under your skin. You don't burn out, you don't break. You keep that color, whatever it takes. I thought that calm was kindness, thought that glow was truth. But there's a colder kind of side.